Hello guys, this is Rico Chandra from JC2Z of Binabangsa School, and today I'm going to discuss one of the paper 4 questions for 9701 chemistry. I'm going to go through this paper exactly as I would do it, in a test, and I'll try to show my thought process all the way through until the end of the paper. So without further ado, let's go on with the paper. So let's take a look at number 1. Iodine is found naturally in compounds in many different oxidation states. Iodine reacts with acidified H2O2 hydrogen peroxide to form iodine and water. This reaction mixture is shaken with cyclohexane to extract the iodine. Cyclohexane is immiscible with water, which basically means that it's not going to mix. Identify the role of H2O2 in its reaction with I- ions in acidic conditions. So basically what it means by acidic conditions is that we're going to find a set of H plus ions in here somewhere in the equation. So it's probably good to note that down. So first, let's identify the role of H2O2 here. We can see that in the reaction, iodide ions become I2. So that basically suggests that the oxidation state is changing. As we know, for an element in its natural state like iodine, the oxidation state is going to be 0. As an ion is going to take the charge, so its oxidation state is -1. So what we're seeing here is that iodine is being oxidized. So that probably suggests that H2O2 is an oxidizing agent. Now, the second part, and I think the trickier part, is that we're going to have to write down an ionic equation for the overall reaction that's happening here. So what we're going to do is we're going to write down first what happens to I minus. So we have I minus, and then it's going to become iodine. So obviously that's not balanced, so we're going to do that to I minus. And we're going to react it with H2O2. And we're going to get water on the other side as mentioned here. So now really what we're going to do is we're going to have to balance whatever is going on here. So here the peroxide ion is actually unique in the sense that it is O2 minus. So that means that the oxidation state of hydrogen is actually going to be reduced because one oxygen here is going to be 2 minus. So if that oxygen is being reduced, it means that we need H plus in order to reduce it. So we're going to add H plus ions here. And then the next step to figure out here is really how to balance the whole equation. So clearly the iodide ions are balanced. The oxygen is not balanced, as we can see. So we're going to try to balance that out by adding 2 here. By adding 2 here, we balance the oxygen here. So right now we have 4 hydrogen on the right hand side, and we only have 2 on the left hand side. So that's going to be a problem. So what we're going to do is we're going to cancel that out with the H plus. So by adding a 2H plus there, we have 4 hydrogens on each side, 2 oxygens on each side, and 2 iodine on each side. And we can also check if this is balanced. What I like to do is I like to check the charges. So I minus and H plus, overall there's 0 charge on the left side, 0 charge on the right side. So it means our ionic equation should be balanced. Okay, next off, we're going to discuss this. So 15 centimeter cube of C6H12 cyclohexane is shaken with 20 centimeter cube of an aqueous solution containing iodine until no further change is seen. It's found that 0.39 grams of I2 is extracted into the cyclohexane, and we find out that the partition coefficient of I2 between C6H12 and water is 93.8. So something we have to remember here is that I2 is a nonpolar compound. So what that probably suggests is that nonpolar compounds like I2 will dissolve better in a nonpolar compound like C6H12. So what that means is, if we're writing it down in an expression, C6, I'm just gonna write it down like this for simplicity's sake. H2O 93.8. So what we're suggesting by this is that this 93.8 shows that this fraction is more than 1. So again, if you remember, if we have something like this, let's say H over, I don't know, oxygen. If this coefficient is more than 1, that means that the thing on top is in more abundance than the thing at the bottom. So here, if we do it mathematically, we could say that the concentration of iodine in C6H12 is 93.8 times that in water. And the reason for that is because, you know, I2 is a non-polar compound. So from this information, we can easily count the mass of I2, which is what we have to work out. So we have to find out the mass of I2 in the aqueous layer. Aqueous basically means water. So how much is there in water? We're gonna do this in terms of algebra. I think it's probably gonna be easier. So 0.39 grams over 15 over x grams over 20 is going to be 93.8. So, you know, if we just work that out mathematically over here, maybe 0.390 over 15 times 93.8 is equal to x over 20. So x is going to be 20 times 0.390 over 15 times 93.8. So this is going to be a very, very small amount that we're going to get. We are going to get, hold on. I forgot my calculator. Hold on a second. Okay. What we're gonna get is 0.005544 grams. And if we do that in standard form, that's gonna be 5.54 times 10, 1, 2, 3 times 10 minus 3 grams. So it's very small, again, because I2 is not polar. Okay, so the next question is gonna be this. So just how the value of KPC compares between hexane 2-one and water, and how it's gonna compare to the value of KPC in the previous question. So basically what it's asking is we are going to compare the KPC of this expression, CH2, 3, COCH3, and we're gonna compare that. So we're gonna compare this to C6H12 and H2O. Okay, so if we're gonna notice anything here, it's basically that the bottom is the same, so that's not gonna affect the partition coefficient at all. What's gonna affect it is the thing at the top. And C6H12, just to draw out the shape, is a very, very non-polar compound. Meanwhile, for hexane 2-one, it's actually a bit polar because you have that ketone functional group. So what that means in our answer is that iodine is actually going to be less soluble in hexane 2-one. The reason for that is because simply it's more polar than cyclohexane. So since iodine is a non-polar compound, it's not going to translate well into hexane 2-one. It's not going to be as soluble. So we're going to write KPC would be lower. Again, it would be lower because less would dissolve in the hexane 2-one compared to C6H12. The reason for that is because hexane 2-one is more polar than cyclohexane. So iodine is obviously less soluble in hexane 2-one. All right, I guess time to move on to the next question. All right, so in this question, we're actually going to be dealing with one of the earliest topics that we had in A2 chemistry. So define the enthalpy change of solution. So if you remember, solution, it's just like, dissolving salt or making a salt solution. So you're going to go from a solid state to an aqueous state. So if we're going to use the proper term, we're going to define it as the energy change or the enthalpy change when 1 mole of a solute dissolves. Again, it's dissolving in water because it has to be aqueous. Aqueous means water, in water. And something that, even I forget quite a lot is this last part, which is to form a solution of infinite dilution. Infinite dilution. And what we mean by dilution is not, delusion like delusional. What we mean by dilution here is, when you add more of the solute, it's not going to dissolve. So that's the enthalpy change of solution. Okay, so next one, I think this is actually easier and a funner question. Basically, we're going to figure out what the enthalpy change of solution of potassium iodide is going to be. So, what I would probably write out here is just the equations themselves so that I could, easily figure it out. So, and then here we can write out the ions. So here we're actually gonna have our delta H of solution because it's from solid to the aqueous state. So here you can solve it like you would for a vector. So basically, how would I easily explain this? I guess, the easiest path would be to do this. So the enthalpy change here in the opposite direction, from aqueous to gas and from gas to solid is gonna be the same as delta H sol. It's basically just like, what you would do in your maths. It's like vectors. So we're gonna do that. I'm just gonna plug in the numerical value here. Plus, hold on. My bad. It's actually the other way around. So what we're going to do is actually reverse this. So Kis to K plus and I minus aqueous is delta H sol. We could also take a different path and instead, go to gas first and then go to aqueous, and then it will still be the same energy change as delta H of solution. So we're gonna write that expression. So that's gonna be minus 629 minus 322 minus 293, and that is gonna give us a value of plus 14 kilojoule per mole. So plus 14 kilojoule. Also don't forget to write the plus so that it's not ambiguous and the examiner knows exactly what you mean. So just the trend and the magnitude of lattice energies of group 1 iodides. So if we're going to pull up the periodic table, basically what we're going to see is that the sizes here are actually increasing. So Li would be the smallest and a second smallest, Ki the biggest. So again, we have to remember first what lattice energy mean. In an expression, it would be, something like this. It's going to be X, Y, S. So here what we actually see is that there's an ionic bond that forms between X and Y. So therefore probably what we're gonna explain this in terms of that ionic bond which we just identified. So there's a trend where from Li to Na to Ki the size is getting bigger. So if the size of the ion is getting bigger, Again, this is just for illustrative purposes. It's not actually like this. We can see it's, Na is smaller, let's say. That means that Na has a lower volume, and that means that the charge density is going to decrease down the group, because as you get a bigger volume, the charge is more spread out, it's less dense, less concentrated. So what that suggests is the magnitude of our lattice energy is going to be smaller, because that ionic bond, or the attraction, the electrostatic attraction between the ions, is going to be less. So that's actually our answer. Charge density of cations decreases from Li plus to K plus. So the lattice energy becomes less exothermic. Again, what we have to remember is that the magnitude decreases, but it's still going to be negative, because lattice energy is always negative. So it's going to be less exothermic, and that is due to weaker electrostatic attraction between ions. All right. So on to the next. Wow, this is a long question. The concentration of Cu2 plus can be determined by reaction of Cu2 plus with I minus. The I2 produced in reaction 1 is titrated against a solution containing thiosulfate. So this is actually a question that is quite common in paper 3, the practical part of AS. If I'm not mistaken, this is called Iodometry. I can't really remember. But basically this is a titration, and I would say in titration questions you'd have to be very, very careful. So we're gonna we're gonna check the question very slowly here. So a 25 cm cube portion of a Cu2 plus solution reacts with excess I minus. The end point is when 22.3 centimeter cube of this thiosulfate is added. So we're gonna have to find out the concentration of Cu2 plus in the original one. So honestly, this is probably going to be easier if you work it backwards, and that's probably the only way that you could solve it. So we're gonna figure out the moles of thiosulfate first, and then from that we can actually work our way backwards, because from the moles of this we could know the moles of iodine, and that iodine happens to be the iodine that was produced here. So if we know this concentration, then we could determine this concentration. So we're just gonna do that. So we're gonna do NS2O3 2 minus is equal to 22.3. This is to convert it into convert it into decimeters. So the moles is gonna be 3.345 times 10 minus 3. Then here, this is where we can work our way backwards. So the mole of S2O3 2 minus, we can use stoichiometric coefficients here, is going to be equal. So the mole of S2O3 2 minus, there's double of that here compared to I2. So this is, 2 times I2. And then the mole of I2 is gonna be the mole of I2 is half of NCU2. So what we can do is we can plug this here. So it's gonna be 2 times half. So the mole of I2 is half of Cu2. Just like algebra, we could substitute it into here. So it's going to be 2 times half NCU2. So it means that NS2O3 2 minus is equimolar to the mole of copper that we have. Sorry, this is U2 plus, my bad. So basically, this is already the moles of copper 2 plus, sorry. So the concentration is just going to be, you know, the moles over the volume. So 3.345 times 10 minus 3 mole. And we're going to, again, the unit here is in Iodometry, so we're going to have to, you know, convert that. Okay, so we're gonna get a value of 0.1338, which rounds off to 0.134 in significant figures. All right, so identify a suitable indicator for the titration. So here, yeah, obviously you could just memorize this, but I think there's something important about knowing what's actually going on here in the reaction. Basically, what we're doing here in the reaction is we're adding this thiosulfate to react with the iodine. So it means if we need an indicator, it's either going to be an indicator that detects 2I minus or detects iodine. If it's an indicator that, you know, detects iodine, it means it's gonna change its color. So if we can, you know, remember an indicator that reacts with iodine, that reaction is going to be starch. So you know, if you can remember from, you know, maybe primary education, the test for iodine is actually starch, because if, you know, you have iodine, then the starch is going to be blue, otherwise it's going to be yellow. So that's essentially what's happening here in the reaction. The moment that iodine, you know, disappears, that means there's no more starch. So starch. Okay, so we're gonna be moving on to the next question. Draw the shape of a 3dxy. So 3dxy, how I like to remember this is you know, in terms of the axes. So if it says x and y, it means the axis that's being used are x and y, so it has to use those planes. So I'm a really bad artist, but more or less this is what it's gonna look like. So basically what it's doing is it's occupying the x and y axes. I guess that's all to be said there. Next we're gonna do this is about catalysts. So here, again, you could memorize this, or you could just try to figure out, you know, what's happening. I like to figure out what's happening in the question. So write equations to show how Fe3 plus is going to catalyze this reaction. So Fe3 plus, if we can recall, Fe has two main oxidation states, either Fe3 plus or Fe2 plus. So that means Fe3 plus is going to be reduced in this reaction, and then because it's a catalyst, the Fe is going to be oxidized again to be Fe3 plus. So we're going to do that one by one. If Fe3 plus is initially going to be reduced, that means something else is being oxidized, you know, for the redox reaction to happen. So we need to find out what's being oxidized in this reaction. What's being oxidized is iodide ions, because the oxidation number from -1 to 0. So it means the reaction with Fe3 plus is going to be with 2I minus. So here we have to figure out what's going to be on the other side. Again, as I mentioned, the only other state of Fe that we have is Fe2 plus. So that means we just have to find a way to balance this whole equation now. You could work this out in terms of electrons, I guess. Basically what's happening between here is that each I minus loses, you know, one electron. So it means overall in the reaction, 2 electrons have to move between Fe3 plus, Fe2 plus, and 2I minus and I2. So basically, if each I minus loses E minus electrons, it means Fe3 plus is gaining electrons. So in order for, you know, there to be 2 electron movements for Fe, then we could just simply balance it out by adding a 2 there. So there's going to be 2 electrons moving. And if you check the charges, 2 Fe3 plus is 6 plus, and 2 I minus is minus 2. So 4 plus charge and 4 plus charge on the right as well. So it's perfectly balanced on that end. Now we have to figure out how the Fe2 plus is going to be oxidized back, because you have to remember this, how this catalyst works is that when you have the overall reaction, it's going to cancel out. So it means we need another equation, but this time Fe2 plus is going to be on the right side so that you can cancel it out. If Fe2 plus is on the left side and it's going to be Fe3 plus on the other side, it means this time around iron is actually being oxidized. So it means we need to find what's being reduced. What's being reduced here is this ion, S2O8 2 minus, is going to be reduced. So we're going to write that down. What's actually being reduced here is the sulfur. So here the oxidation state is going to be plus 14. So each sulfur has an oxidation state of plus 7. Here it's going to be plus 6. So 1 electron moves between each sulfur ion. So we know it's going to be reduced into that. So again here, one electron is being gained. So it means that there has to be an electron lost from there. So again, we need a net movement of 2 electrons. We're gonna just, you know, add a coefficient of 2 in front. It's gonna be perfectly balanced. Just for demonstration purposes, you know, we could cancel this out, cancel this out, cancel this out, and cancel this out, and it's gonna be exactly the same as the reaction on top. Okay, so we're gonna move on to the next question. An orange precipitate of HDI2 forms when Hg2 plus ions are added to Ki. The solubility is this much. So we're gonna find the solubility product. This is maybe one of the trickier questions, but as long as we can, you know, remember the equations of KSP, it's gonna be easy. So I would probably think of this in terms of KSP's definition. So really KSP is the solubility constant, so it means equilibrium constant for a solid that is dissolving in an aqueous solution. So, you know, basically just suggests, you know, how much a certain substance is soluble. So KSP equals Hg2 plus and I minus squared. We're gonna add squared here because in the overall reaction for KSP, you know, for demonstration purposes, for learning purposes, I'm gonna draw it out. We're gonna draw out the solubility again. So Hgi2 minus is gonna be Hg2 plus and 2I minus. So our KSP is gonna be, you know, Hg2 plus and 2I minus over HgI2. But again, we have to remember HgI2 is actually a solid, so no concentration. If it's a solid, there's no concentration because it's not dissolved in anything. So our KSP is just this. Sorry, messed up their square here. So this is exactly like you would write, you know, equilibrium constant, you know, back in AS. So that's what KSP is. We're going to calculate the solubility product. Basically what the solubility of HgI2 here says is that, you know, for, you know, each molecule of, sorry, for each mole of HgI2, I guess, you're gonna get this much. So I think it's just gonna be much more easier to understand when I draw it out. So basically HgI2, so for every so basically in 1 decimeter cube of HgI2, you're gonna find 1 times 10 minus 7 grams of it. So I think it's gonna be much easier for us to do it in terms of moles instead of grams, because here in the concentrations, we're measuring it in mole per dm cube. So if we're gonna convert that, it's just gonna be our mass over mr as usual. So that's gonna be basically 2.2 times 10 minus 10 mole per dm cube. And now we're gonna have to figure out how to work this out. So if you have 2.2 times 10 minus 10 moles of this HgI2, it means that we have 2.2 times 10 minus 10 moles of Hg2 plus, because this is in a 1-to-1 ratio here. So this 1-to-1, that means that for every in 1 decimeter cube, you're gonna find 1 mole of HgI2 dissolved. In 1 mole of HgI2, you also find 1 mole of Hg2 plus. So that means that we have a concentration of Hg2 plus that is like this in 1 dm cube. Another thing that we have to figure out is then the concentration of I minus. We don't have that. But that's actually very easy to figure out, because from this equation, again, the concentration of I minus is double. So for every mole of Hg2 plus, you find 2 moles of I minus. So really, the concentration of I minus is just 2 times Hg2 plus. So if we're gonna plug that in into here, like algebra, we're gonna get an expression like this: Ksp equals 2 Hg2 plus squared. So it's gonna be 4 Hg2 plus cube. So really easy. We're gonna mathematically do that. Just gonna plug that into the calculator. We're gonna get 4.259 times 10 minus 29. We want that in 3 significant figures, so it's gonna be that. So this is not a very soluble compound, to be honest. We're gonna have to figure out the units. So we can figure out the units from here. So the unit of this is gonna be mole per dm cube. Here is gonna be mole per dm cube, but we square this concentration, so we multiply those, and we're gonna get mole cube dm minus 9. All right, we're finally here on number 2, and this is gonna be a thermodynamic question. Silicon is the second most abundant element by mass in Earth's crust. In industry, silicon is extracted from SiO2 by reaction with carbon at over 2000 degrees Celsius. Explain why the entropy change of reaction 1 is positive. Okay, so frankly speaking, this question should be quite straightforward. How I like to remember entropy change, which is not the official definition Cambridge gives, but entropy change is basically the level of disorder that a system has. So here you have 2 solids on the left hand side, and then you have a liquid and a gas. Simple physics says that liquids and gases are much more disordered. They're less packed together than solids. So basically, in terms of the change of the level of our disorder, delta S is going to be increasing. So I think that should be a sufficient answer, to be honest. So 2 solids turn into a liquid and gas, which have higher entropy because they are higher in energy and have more different possible arrangements. All right, so next reaction 1 is highly endothermic. If it's endothermic, it means that your enthalpy change or delta H is positive. The question is suggest the effect of an increase in temperature on the feasibility of this reaction. So again, we have to remember that feasibility is related to Gibbs constant, where Gibbs constant is defined as delta H minus T times delta S. So if it is a very endothermic reaction, that means if it's very endothermic, it means that the reaction was not feasible to begin with, but because you increased the temperature, actually scratch what I said. A highly endothermic reaction just means that you need more temperature for it to occur. So therefore, if you see an increase in temperature here, where delta S is constant, delta H are constant, if T increases, then this whole value is going to be smaller. And if we remember, the smaller or the more negative delta G is, the more feasible the reaction is. So we could write as T increases, T delta S becomes more positive. So delta G becomes more negative, basically. So more feasible. All right. Honestly, I think this should do. All right, next question. Use the data in table 2.1 to calculate delta S. This should also be a pretty easy question, because delta S, you calculate it exactly the same way as you would calculate delta H, and we've been doing that since IGCSE, so should be pretty easy. We're gonna just do delta S equals S final minus S at initial. So we're going to compare the final entropy to the initial. That's going to be our change. So in the final, we have two compounds. That's going to be SiHCl3, so 314, plus, what is that, H2, 131, minus 19 plus 187. All right. Plug that into the calculator. We're gonna get oh, sorry, just realized an error here. You have 3 HCl, so you have to multiply that by 3. That's why I was confused about the value I was getting. It was very big. All right, this should be the correct value, so it's going to be minus 135. Okay, next, reaction 3 is the reverse reaction of reaction 2, and it is used to obtain pure silicon. Use this information and your answer in BI to calculate the temperature at which reaction 3 becomes feasible. If you were unable to answer, you should use delta S, since I think we got the proper answer for the first one. We don't have to use this value. Okay, so something that we have to be very wary of here is, because this is the opposite reaction, delta S is going to be the reverse. So it's going to be positive 135 actually. And we need to find where it becomes feasible. So remember, for feasibility, delta G has to be less than 0, where delta G is delta H minus T delta S over 0. So we can work this out like in maths. So our T is going to be greater than delta H over delta S. T is going to be greater than delta H delta S. So that's going to be 219.3 times 10 power 3 joules. Note that I'm converting this to joules because our delta S value is in joules. So, oh wow, this is a high temperature. We're gonna divide that by 135. So we're gonna get, again, I apologize if this is a little messy. Usually when I'm practicing, I do it quick, like this, so that I get used to doing it in a test. So the temperature is going to be 1624 K, and that's it. Silicon can also be produced by electrolysis of SiO2 dissolved in molten CaCl2. The relevant half equation is shown. Calculate the time in seconds to produce 1 gram of silicon by electrolysis using current of 6 amperes. Frankly speaking, this is quite a hard question, for me at least. Yeah, I would just advise to be very careful when doing these sorts of questions. So we're gonna find the time to produce 1 gram, but we need to find an equation that relates how much we're gonna get in the first place. So I think how I would do this is first to figure out how we're going to use Faraday's constant here. The reason for that is, I think the Faraday's constant is one of the only constants that relates charge to mole. And note, when the unit is charge over mole, it means mole of electrons. So it means that if we have 4 electrons, then the charge that we need is going to be 96,500 times 4. So hold on, 96,500 times 4. So 386,000. Sorry, 386,000 coulombs. And then we have a current of 6 amperes, which is 6 coulomb per second. So so basically what this means is you need 386,000 coulombs per mole of Si. Because to produce 1 mole of Si, you need 4 moles of electrons. And here we actually already have a sort of expression here. You have, your current, you have your charge needed for each mole of silicon. So I think it would be better if okay, so if we're getting 6 coulombs per second and we need 386,000 coulombs to make 1 mole of Si, we could figure out the time needed for producing 1 mole of Si. So charge is current times time, and time is charge over current. So we're gonna get 386,000 over 6. This is Cs minus 1. This is C, and then this is mole of Si. So we're gonna cancel that. It's gonna take us 386,000 divided by 6. It's gonna take us 6,433.3 seconds to make 1 mole of silicon. And to produce 1 gram, then it means we need 1 over the MR of silicon. The MR of silicon is gonna be 28.1. So we need, how much is that? We need 0.03559 moles. So basically what we could do here is 0.3559 times 64333 equals 2.289 seconds. We're gonna round it off to 2.290 seconds. It's only worth 2 marks, but it's a tough question in my opinion. If you were confused by what's going on, I'll briefly re-explain. Basically, what's going on here is we need 4 electrons to produce 1 mole of silicon. From Faraday's constant, we know that to generate the 1 mole of electrons, then we need this amount of charge. So we multiply that by 4 to get the charge for 4 moles of electrons, and 4 moles of electrons gets us 1 mole of silicon. So this is why I wrote per mole of Si. We have a current of 6 coulombs per second. So it means each second we're producing 6 coulombs. From this physics equation, we can convert it time equals Q over I. So this is going to be the time needed to make 1 mole of silicon. Because we only need this much silicon, that's going to be 0.03559 mole times mole Si times what we had here. And what's going to happen is these are going to cancel out and you have the time here. So I apologize if that was confusing. I'm not very good at explaining these sort of topics, but I think you should be able to figure out what's going on here. Alright, so next we're going to move on. This is a transition metal question. So you should probably already have this memorized by the time the A2 comes out. Basically, a transition element is just a D block element, so it's from the D block, which forms stable ions with incomplete d orbitals. So identify 2 typical properties of transition metals. Probably they have variable oxidation states. And usually they form colored compounds. Either that, or you could probably also say that transition elements form complexes. This is just extra. And other than forming complexes, they can also behave as catalysts. All right. So we're gonna go on to the next question. TiO2 plus is a colorless ion. Suggest why. I think we could, take a look at the periodic table for this. I'm sorry that I can't pull up a copy right now, but I'm looking at mine, and basically Ti is gonna have this electronic configuration. So it's gonna be Ar, and then 4s2, and then 3d2. So here, explain why TiO2 plus is a colorless ion. Again, we have to remember the cause of color in the first place. The cause of why transition elements have color is because of electron promotion. So basically what happens is you have an electron that's in a lower energy state, and then you promote it. That causes a wavelength to be absorbed, or a frequency of color to be absorbed, and then one color is missing from the spectrum, and every other color in the spectrum forms the complementary color, and that is what the human eye sees. Basically what that means is that you need electrons in the d orbitals to be promoted in the first place. And Ti in this state is actually Ti4 plus. How do I know that? We can figure out the oxidation number. O is 2 minus, the charge is 2 plus, it means Ti is 4 plus. So it means it already lost all of its d electrons. So essentially it's empty. So TiO2 plus has no d electrons. So it does not absorb photons for electron promotion. So no wavelength of light is absorbed. Okay. Next question. Give the electronic configuration of an isolated Ti3 plus ion. I would usually do this. I would write down the normal electron configuration first. Again, always refer to the periodic table when you're doing this. 2s2, 2p6, 3s2, 3p6, 4s2, and 3d2. But what we have to remember is that when when Ti becomes Ti3 plus, it means it loses 3 electrons, and we have to remember always the transition metals lose from 4s2 because it's in a higher energy level. So this gets removed first, and then we take 1 electron from there. So the final electronic configuration is going to be that. All right, next question then. Write an ionic equation for the reduction of TiO2 plus by zinc metal in acidic conditions. Again, as I mentioned earlier on in the video, acidic conditions just means there's H plus involved in the reaction somewhere. So write an ionic equation for the reduction of TiO2 plus. So here it says it's going to react to form Ti3 plus. So it means we don't know what's going on in the reaction, but this is what we know for now. And we know what happened here. We know that it's reacting with zinc. We know for a fact actually that zinc actually forms 2 plus ions only because it has a full D subshell. So we know that if TiO2 plus is reduced, Zn must be oxidized, and it oxidizes perfectly into Zn2 plus. Again, it said acidic condition, so it means somewhere here there's a transfer of hydrogen. Probably the reason why that's happening is because there's oxygen here. So if there's oxygen, we have hydrogen. Probably means that we are forming water to balance that on the other side. And now the only problem here is that we are still unbalanced in terms of charge and also in terms of hydrogen. There's no hydrogen on the left hand side yet. So we're going to try to balance that out by adding H plus. Now it's a question of how much do we need to balance. Oh, and actually before that, sorry, I forgot. From Zn to Zn2 plus, we have a movement of 2 electrons. So it loses 2 electrons. It means that from TiO2 plus to Ti3 plus, there must also be a gain in 1 electron. But in this case, it is actually only gaining 1 electron. So to make it so that it's gaining 2 electrons, we can do that. And then now we just have to balance out the oxygen. So we need 2 water, and therefore now we can balance the hydrogen. Just to check, if it's balanced, this is 4 plus, this is 4 plus, 6 plus, 8 plus. So perfectly balanced on both sides. Just for demonstration's sake, I did that in terms of electrons. You can also actually do that in terms of oxidation number if you really wanted to, like that. So if there's a gain in 2 oxidation numbers there, it means there should also be 2 between those. So that's why you multiply it by 2. I hope that makes sense. Okay, so now we're going to be looking at an electrolysis question. Basically it's asking you to figure out the half cell, the half cell potential, and the only information it gives you is the standard potential of this, and also the Gibbs constant, or the change in Gibbs. So if you can recall, delta G is equals to negative NFE. So we can actually figure out E cell by doing delta G minus NF. So N is the number of electrons involved in this reaction. If in the reduction it means there were 4 electrons involved, then surely it means in the oxidation 4 electrons were involved. It's never that 5 electrons are happening on one side and the other side has 2. It's never like that. 4 electrons on one side, the other side will also have 4 electrons going on. So what we're gonna do here is negative 436 100 joules divided by negative 4 times 96 500. Again, the reason why I'm converting this into joules is actually because of the unit of Faraday's constant and E cell. So F times E is gonna be coulomb per mole times volt. So it's actually joule per mole. So it means our delta G is actually in terms of joule, not kilojoule. So again, be careful with that. If you write it wrong, you're gonna get a really weird answer. So I'm gonna plug this value into my calculator, and we're gonna get a cell potential of this much. We can remember that E cell is E cathode minus E standard anode. Okay, now what we have to figure out is which cell is the cathode, which cell is the anode. A really handy trick that I use to remember if reduction happens at the cathode or the anode is I write down red cat, which basically means reduction happens at the cathode. Another way that you could probably look at it is that positive ions are attracted to the cathode, and the reason for that is because it's going to be fed electrons. So 2 ways to remember where reduction happens. I like this because it's very easy to remember. But anyways, back to the question. You can see that O2 is on this side. And you can see here that Ti is going from 3 plus to 4 plus. So what that means is that Ti3 plus is being oxidized. So this half cell is the oxidation cell, which means it is the anode. Here we can do it algebraically. So we're gonna do 1.129 volts minus, what's that gonna be, 1.129 volts, sorry, it's gonna be 1.23 volts minus 1.129 volts. So I'm gonna plug that into my calculator, and we're gonna get 0.101 volts. So positive 0.101 volts. Okay, next question. When aqueous citrate ions are added to Ti3 plus, the complex forms. I think this is a 1 mark question, but I think it's probably safer if you write down 2 points. So the reason why it can form complexes is because in its d orbitals there are spots which are empty or vacant. That means electrons can be donated to those orbitals, and these orbitals are energetically accessible. Basically what that means, what's a good way to explain this? if it's energetically accessible, it means that, you know, it can bond easily without using, you know, a lot of energy. So basically, yeah, that's the answer. So Ti3 plus has vacant d orbitals and they are energetically accessible. Basically, I guess a better way to say it is energetically accessible means the MTD orbitals are, you know, not that high in energy, so they can easily accommodate a lone pair that's coming in. Okay, so we're gonna take a look at this question now. This is still related to electrolysis. So basically what it's saying is this does not react with oxygen dissolved in water. You know, for reference, this is oxygen in water. So if the reaction doesn't happen, again, we remember that it's in terms of Gibbs. So, you know, delta G is more than 0. It means E is less than 0 because delta G is negative N Fe. So it's you know, the opposite sign. Ti3 minus. So again, you know, this standard potential is given in this form, but what's reacting is this. So so on the wrong side, we have to flip it. So it means this is being oxidized. So what it's saying is the oxidation cannot happen. So it means you know, in terms of the oxidation, if it's the oxidation, it means this is Re anode and this is Re cathode because you know, reduction happens at the cathode. So E cell equals E cat minus E anode. So E cell again here is less than 0, so it means E cat is less than E anode. Now, as I mentioned, E cat is 1.23. So just off this expression, it means E anode must be bigger than 1.23. So the potential must be greater than 1.23. Then 1.23 for E to be less than 0. Right? I think that should be good. Okay, so next question. This is about transition metals. This should be a free mark. I highly advise you memorize the definitions because really they are free marks. Basically, coordination number is just the number of coordinate bonds that are being formed by the metal. Okay, so write an equations for the formation of TiF6 to minus from TiO2. You know, here if you're noticing, it's getting F from HF, so it means that's what we're reacting with. So TiO2 plus 6HF because, you know, there's 6F there. And that's gonna be TiF6 2 minus. Reason is because Ti is for plus, HF is minus 1, so you're gonna get overall 2 minus. And then you're gonna balance up the oxygen, so you're gonna have some water, and then you're gonna have H plus as well. This is a perfectly balanced equation because the charge on the right is 0, charge on the left is also 0. Alright, what is meant by bidentate? So again, if you have bidentate, that's something like your, you know, En or your EDTA ligands. Sorry, EDTA is polydentate. Let's just do En, or this also works, this compound. Forgot what this is called. Hold on, let me search it up. this is an oxalate, so this is an oxalate ion, so OX and EN. As you can see here, they have two lone pairs which connect to a central metal atom. So that is basically all that a bidentate ligand is. So a species with two lone pairs that form two dative covalent bonds to a central metal metal atom. All right. Okay. So. Okay. Okay. So basically, what this question is asking is for us to draw out the other stereoisomers. So this is, one of the isomers. We have to draw two more because again, this has cis-trans isomers and optical isomers. I think first, probably what would be really easy to do here is to draw out what the trans ions would look like. So I would probably start off with that. It's going to be much easier. Cl. So this is going to be our other ligand. I'm not sure what that's called. Okay. So that's our trans. Again, these are in opposite directions. So, it's trans. This one is the optical isomer. So it's going to be a mirror image. So it's going to be like, the exact opposite of this. So, if you were, to have a mirror over here, then you would draw out what you'd see on that mirror. So even, this black wedge and these, dotted lines, they're going to flip as well to the other side. It's like that. And then the Cl is, it happens to be in the middle, so it's going to be exactly the same. And I think we should be done with this question, yeah. So the ion is symmetrical. Deduce which of the following are polar. Okay, so if it's so I think here it would probably be best for us to determine something. Deduce which, if any, are so actually, okay, I think it's better if we just draw where the charges would be going. So this is an anion, so most likely it's going to be, electron withdrawing, but I wouldn't be too sure about that, so we're just going to do it in terms of Cl. So it's going to withdraw. So here what we're seeing is here the charges cancel out because they're pulling it, exactly away from each other, so it cancels out. Here there's it's both pulling in the same direction. Honestly, I'm not too sure what it means by symmetrical here, but probably what it's suggesting is that, it's non-polar or something like that. So regardless of that, we can see that, Cl is pulling away same direction. There is almost no way that this pulls, exactly the same as Cl or pushes, there's no way it pulls as much as Cl. So I would say stereoisomer 1 and 2 are polar. I guess the easiest way is because the dipoles do not cancel out. Okay, so we're finally on to organic chemistry here. Okay, so F and J both contain the arene functional group. Identify the other functional groups. So here we have a carboxylic acid, that's an amine, so amine and carboxylic acid. Here we have a phenol, an ester. Obviously this is an alkane, I guess. These are alkyls, but I think probably just writing these two are sufficient. So we have a phenol and then ester. State the number of chiral centers. Again, chiral center means something with 4 different groups. Here, I don't think any of the carbons even have 4 groups, let alone 4 different groups. So I think it's 0 here. Here, this is not chiral because these are identical, but this is chiral because there's going to be a hydrogen there, and it has, you know, different groups on each side. This is also going to be chiral because you have a hydrogen there. It's going to be different. Nothing in the benzene ring is going to be chiral. This is definitely not chiral. I don't think anything else is chiral, so there's going to be 2. All right. Okay, so this is going to be a synthesis question. These questions could be hard if you don't remember your reagents well, but as long as you memorize them, it's going to be pretty easy. So here, what we have is a Friedel-Crafts alkylation, one of the most basic reactions that we learned. So it's just going to be CH3Cl, and we're going to have AlCl3 as a catalyst. I think I'll write that down. Catalyst. This is our halogen carrier. HNO3, H2SO4. That's going to give us, you know, obviously nitration. But what we have to remember is where it's going to be directed. So because an alkyl is an electron donating group, it could go here, here, or here. Here in the next step, we can already see that it's at the bottom. So that's what we're going to draw out. Okay, so one last question to fill out here. Okay, basically it's asking how you can convert from this, from nitro to an amine, and how you're going to do that is you're going to do hot tin with concentrated HCl followed by NaOH. All right. So this is going to be a different synthesis. The student changes the order and the conditions are used. The reaction is shown. Okay, so basically, this is the only difference here is that instead of an alkyl here, you have a carboxylic acid group. And if you can remember, carboxylic acids are going to be an electron withdrawing group because the CO bond is a really, really good pulling part. It's going to be really, really good at, you know, pulling electrons away from the ring. So because it's a EWG, electron withdrawing group, you could pull it here or here. So anyway, which your heart likes is fine as long as they're in this position. So I put it this, you know, there. The reason is because see, hold on a moment. Yeah, because COOH is electron withdrawing, which activates position 3 and 5. Okay, so we're gonna move on to the next. J reacts under suitable conditions with NaOH after acidification. Compounds K and L form. Give the molecular formula of L. So this is actually just hydrolysis. J reacts in after acidification. Okay, so it's gonna, you know, form NaOH, react with NaOH first to have that hydrolysis, and then you're gonna add an acid. The reason why that acid is going to be important is because when you react with Na, this part is actually supposed to be Na plus, but the HCl substitutes that and it reacts. So what we're left with on L is actually this compound. So okay, basically we can count the hydrogens. I think that'd be good. There's gonna be 1 here, 2 here, 3 here, 3 here, 2 here, 1 here, 1 here. Almost forgot. 1 oxygen, 6 carbon. Sorry, not 6 carbon, 9 carbon. So C9, and then on hydrogen we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. This is 2, so 16. 17, and then you have 1 last one there, 18. So C9, H18O. State the 2 types of reactions that occur when J reacts with NaOH. Okay, so we can actually have acid base. Reason is you could react easily with that. So you have acid-base reaction, and then the reaction which we just witnessed was hydrolysis, so that's the other type. K can also be synthesized from a phenol. Write an equation for the formation of M in reaction 1. So that's actually going to be pretty easy. So it's just going to replace the H, so we're just going to get C6H5 O minus and A plus half H2. Draw and the production. Okay. So here we have to note that there's going to be an excess of bromine. If that is in excess, it's going to enter all the activated positions. Again, remember that OH is a donating group, so it's going to be 2, 4, 6. Explain why phenol is a weaker acid than K. So that's going to be a 2-mark question. Phenol is like a weaker acid. Okay, so the reason why phenol is a really weak acid, even though it is acidic, is because of why phenol is weaker than K. If the question asks you to explain, why phenol is weaker, you can explain why phenol is weaker or why K is stronger. Here, I'm just going to explain in terms of phenol. I think it's going to be easier. So, the phenoxide ion is, the phenoxide anion is less stabilized compared to the COH group. That's one way to explain. Another way is you could say the COH bond is stronger or harder to break because of electron delocalization, or you could also say electron overlap, which causes a partial double bond character. Explain why the reagents and conditions for these two reactions are different. There's a couple of ways to explain this, but I would probably explain it in terms of the benzene ring. The reason is that benzene is actually very stable if there's no electron groups. So how I would start explaining this is just by introducing the concept of the benzene ring that I mentioned at first. In phenol, a lone pair is delocalized into the ring against electron donating group is delocalized into the ring. This causes it to have a higher electron density, hence it attracts electrophiles better. Simple as that. Okay, on to the next. 2-chloropropanoic acid is used in many chemical synthesis. An equilibrium is set up when 2-chloropropanoic acid is added to water. Write the equation for this equilibrium. Okay, so what we're gonna write here is, what we usually write for demonstrating the properties of a weak acid, because this is, a weak acid. So C3CH Cl COOH plus H2O, reversible because it's a weak acid, CH3 CH2 plus H3O plus. Okay. So this is going to be an equilibrium question, one of my favorites. Calculate the pKa of CH3 CHCl COOH. So what we have to remember is pKa is minus log Ka. Okay. So that means we have to figure out the Ka first. pH is minus log H plus, and Ka is going to be H plus squared over the concentration of the acid. Okay, so I would figure out the concentration of H plus first. So H plus is going to be 10 power minus 1.51. And then we have the concentration of the acid right here. So 0.150 over 250 over 1000 times 10 minus 1.51 squared. So it's gonna be, I'm gonna plug that into the calculator. 0.150 oh, hold on. Hold on for a moment. My calculator is not working. Is there something I did wrong? Hold on. 0.150 pH. Look, 10 power. Oh, sorry, my bad here. Yeah, so log H plus is going to be 10 power negative 1.51. So that's going to be a very small value, 0.0309. We're going to square that value, and then we're going to divide it by 0.150 divided by 0.25. That's going to give us 0.001592. So pKa is just going to be minus log of that. So it's going to be minus log, minus log answer. It's going to be 2.798, which rounds off to 2.8. An equal concentration of aqueous propanoic acid has pH 2.55. Explain the difference in the pH of equal. Okay, so basically it's just asking you why propanoic acid is less acidic, because it has a higher pH, means it's less strong of an acid. Basically that could be the first part of your answer, and then you could explain why that is so. So I would just say CH3 CHClCOH is a stronger acid. It gives off a higher concentration of H plus, and then you could explain why. This is due to the electron withdrawing effect of Cl, which weakens the COH bond. So H plus is given more readily. Okay, alanine is an amino acid. Honestly, I don't like amino acids. It's a pretty tough topic. But anyways, state what is meant by isoelectric point. Isoelectric point is basically the pH where the molecule has no overall electrical charge. Give the structural formula of alanine at pH 2. If it's at pH 2, it means it has very acidic properties. So that probably suggests that it probably has gained one positive hydrogen here in the NH2. So we're gonna write it down: CH3, C, NH3 plus, and COH. Alanine exists as a pair of optical isomers. The structure of one isomer is shown. Okay, so again, this is very similar to what we did up top. It's gonna be a mirror image. If you don't mess up on these, this could be a couple of easy marks to score. Let's just do it like that to show it's mirrored. I would also do, oh sorry, this is in the middle, no need to mirror. Okay, everything should be good there. Polymer C forms from the reaction between alanine and 4-amino butanoic acid. Draw a repeat unit. Okay, so this is the part of amino acids that I honestly just do not like. But how you could try to make it easier is instead of immediately trying to get the answer, just draw it out, think about it. There's amino butanoic acid and there's alanine. In terms of the strength of the acid, probably COOH here is going to be a stronger acid, I think. Yeah, it's probably going to be a stronger acid here because it has a longer alkyl chain. So probably you're gonna see that this reacts more readily. Here's what I mean. You're gonna have alanine, which is CCH3, and then you have NH2 here, and you have COOH here, and then you have H, and then you have H2N, CH2, CH2, COO. Oh, sorry, other way around actually. COOH, CH2, and then NH2. So what's gonna react is between these two. Sorry, it's gonna be that, and you're gonna give off water. On the other side here, you're gonna have another COOH coming in here, and that's gonna be from your alanine. It's gonna be from your alanine, COOH here, CH3 and H2. And then this H, sorry, and these two are gonna react again. So you're gonna have another one of these coming on here with the rest of the molecule over there, and then it's gonna react. So yeah, you kind of have to imagine here, so that you don't waste time. But basically, what's repeating is between this group and this group, because here this happens, and it happens again. So it means the repeat unit is gonna be between here. So me personally, you're gonna have another NH2 here, by the way. So it's gonna take that. You have to find the repeat group. Repeat group is a unit which repeats itself. If you notice, there's a pattern of COH connecting with NH2. This time it's from the alanine. This time it's from the what's it called? From the 4-aminobutanoic acid. So if you're gonna draw out the repeat unit as the unit again, which repeats, what Cambridge wants is for you to draw one part of the repeat unit, sorry, here, and then you're gonna draw out the molecule, and then you're gonna have the functional group that was formed. Then you're gonna do CH2, 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 then you're gonna have N, H, C, O, and then if you notice, this is gonna repeat again, and you're gonna have the same structure as earlier. Over here. Here and here, these are the exact same structures. So it means at this point it's just repeating itself. So you don't need to draw that point anymore. Just get that out, connect. This is one repeat unit. Done. It's worth 2 marks. I would still be very careful so as to not lose even marks on this paper. Show the type of polymerization. This is going to be condensation. As I mentioned earlier, water was released. Scientists are investigating C as a replacement for polypropylene. Suggests an advantage of using C instead of what is this? Instead of polypropylene. Yeah, polypropylene means you're gonna make it from propylene. What that means is it's gonna be very, very long. It's just gonna be a bunch of carbons and carbons and carbons, making it very non-polar. So it's gonna be very unreactive. So that's actually a bad thing for our environment because polypropylene is highly unreactive. It can't be biodegraded or hydrolyzed. C can be easily hydrolyzed because of the amide bond. Okay. Next question. Okay. Next question. Basically, we just have to identify the conjugate acid-base pairs. This is nothing special. It's something we've learned a lot in AS. So basically, what I just drew is the base pair already. Again, you have to remember the base pair differs by 1 H plus. So yeah. excess of NH3, CH3Cl, CO minus undergoes a nucleophilic substitution, so SN. A student investigates the rate of reaction of 2. The student makes a CH3Cl minus with an excess of NH3. Use the graph. Okay. So the easiest way to show that it's first order is that there's a constant half-life. So in case in case you didn't know, the actual formula, again, this is not taught in the Cambridge curriculum. This is just for extra information. But basically for a first order reaction, this is the actual equation. So the concentration at T is equal to ln of the original concentration minus our rate constant times T. So basically, basically this is our this is our half-life time. So this is all of it as a constant. Ln half is a constant, minus K is also a constant. So our half-life is constant for our first order reaction. So we just have to prove that. It's easy. So this is 0.0210. We have to find half of that, so that's going to be 0.0105. 105 is going to be around here. And then we have to find the half-life of that again. So 105 divided by 2, that's going to be like 0.525. It's going to be a bit hard to demonstrate, but somewhere around here, I guess, be good. About there, 1000. So again, we're looking at half-lives. So where is it? Okay, here we can already see it. It's basically 500 seconds here. My line isn't exactly the straightest, but you can see it's 500 seconds on both sides. So there's a constant half-life of about 500, what is it, seconds? Yeah, 500 seconds. Okay, next question. Explain why a large excess of NH3 needs to be used in order to obtain. Okay, so how do I okay, basically, first order, second order, that just means the order in which the reaction affects it, right? If NH3 is in a very, very large excess, regardless of whether it was original first order, second order, third order, it's all gonna seem like it's zero order. The reason for that is because if the concentration of NH3 is so big, you use a bit of it, it's basically constant, so it's not gonna affect our rate constant very much. If one of it seems to be very constant, so it's so that NH3 is practically constant, and zero order to test if CH3 CHClO minus is first order. Okay. So, okay, next question. Use the information in the table to determine whether it's SN1 or SN2. Okay, so this is something that wasn't actually covered in our AS, and we kind of have to figure this out for ourselves. But basically, in a SN2 reaction, that's a backside attack, remember? So, what's gonna happen is something's gonna attack from the back, and it's gonna kick out something. SN1, it only depends on this breaking, so how fast that breaks. So basically, SN1 means first order, SN2 means second order. That's all that it really means. So we just have to find out, is it first order with respect to the reaction, or is it not? Here the concentration of that is basically zero, no change at all. So what we're determining is here. This is a little weird because we're not doubling it, we're multiplying it by 1.5. So we can figure that out. Hold on. See, okay. So we already know that it's first order with respect to this. Now we just have to determine if, yeah, so it does show that there is a relationship between NH3 and the other. So it shows that there's a reaction with NH3, and it also shows, we were first order with respect to the other reactant. So that means that we're SN2 because we depend on, two two reactants, and the reaction is overall second order. So here, if you actually calculate that, sorry, I just want to test this. Yeah, so it is first order because the reaction is also first order with respect to NH3 because when it is increased by 1.5, the rate increases by 1.5 times. It means the reaction is second order overall. So SN2. Alright, describe the effect of an increase in temperature on the reaction of CH3CH, ClO minus, and NH3. This is honestly nothing new. We learned this all the way back in AS. The higher temperature you have, you're going to have a higher rate of reaction. So rate of reaction increases. If you remember the Boltzmann distribution, so it's going to be a higher amount that has the temperature needed. So rate of reaction increases because a greater proportion of particles have energy above the the activation energy. Sorry, I forgot the term for a bit. So frequency of effective collision increases. When an excess of this is used, further substitution reactions can occur. The product has the formula. Okay. Give me a sec. Okay. So that's gonna substitute in H plus Cl. This is a little pair. Okay, so basically this the product that's being formed is actually also in excess. That basically means it can react again with what we just formed. So how am I gonna explain this? To see what's going on, basically this is an SN attack. This is partially positive, that gets eliminated, right? So that reaction is just going to happen again because this is in excess. So it means there's more than sufficient to react again. So you're going to react this back to that central carbon atom that we attacked. You're going to eliminate the Cl again. So if I were to draw this out, so at first I had, what was it, CH3 CHCl that was substituted. So CH3 CH CH, okay, then I have NH2 there, then I have C, O minus, something like that. Then we have another one of these where the lone pair is going to attack right there because it's partially positive. So we're going to scratch that. And then how should I draw this? I can draw this out. So minus, and then we have NH here. Sorry, this is really ugly drawing. Let me fix it up a little. So NH, then it's gonna react again. That is what it's gonna look like. All right, so this is gonna be the last question in this whole paper, and yeah, let's get on with it. So first part is basically just write a reaction with SOCl2. How here you have to be a little bit careful because SOCl2 can give a chlorine to either an acid or an alcohol. And here you have a carboxylic acid and an alcohol. So you're actually going to have two chlorines that are gonna substitute in there. So you're gonna have Cl, CH2, COCl. We just released two HOs, so we're gonna have two SO2s and we're gonna have two HCl's. Simple as that. After W and X have reacted, an excess of this is added to the reaction mixture. So after W and X has reacted, we're gonna add an excess of C3, COO, and A to the reaction. Okay, basically, this reaction is addition elimination, which means we're gonna form HCl, right? And for us to do the next reaction, we don't want it to be acidic, because if it is acidic, it could potentially react with the lone pair over there. That's unfavorable. So what we're gonna do is basically explain that. We want to remove excess H plus to avoid unwanted reactions in the future, or like I guess in the next steps. I think in the future is a little bit vague. Okay, so here as I said, it's addition elimination. We're just gonna have to simply draw the mechanism, so that isn't gonna be very hard, I think. You have a lone pair there. This electron withdrawing, this is electron withdrawing, and this is going to be partially positive. This is going to attack right there. The attack is going to continue until the end. We're going to have an intermediate which looks something like this, HH plus and AR. See over there, we have a lone pair over here. We're going to want to stabilize that. We want this to go here, and we're going to want to continue the attack again until the end. Then what we're going to have is we're going to have NH. This is going to be a double bond again, and AR over here. So that's a pretty sweet reaction, if I say so myself. Very neat mechanism. So explain why C2H5NH can act as a nucleophile. Basically, nitrogen here has a lone pair, so nitrogen has a lone pair, which it can do. All right, next on. So this is going to be thin layer chromatography, which is it has a fancier name, but it's really just the the chromatography that we know from primary school. It's just more in-depth. Here, the first part of the question is asking the mobile phase and the stationary phase. So this might sound a little bit confusing, but basically the stationary phase is, yeah, you know, in chromatography, if you do it in a lab, you're gonna have like a very thin stick called a spotter. Let's say you have a sample of something, you're gonna dip the spotter into your sample, then you're gonna stick it there onto your base here, the baseline on your chromatography paper. And that's all the stationary phase is. Basically nothing is moving yet. We call that the stationary phase. There are two things that you usually could use for the stationary phase. The most common is silica. You could also try to use aluminum oxide, but we're gonna stick with silica just because, you know, in the real world, this is the most commonly available. Here it says ethyl ethanoate is the solvent. So the mobile phase is when things start to move, and things only start to move when there's a solvent that carries the substance. So it means this is ethyl ethanoate. Ethyl ethanoate. So describe how RF can be calculated. Basically, RF is distance of solvent front over, you know, the distance of our sample. So sorry, other way around, sorry. Distance traveled by our sample divided by distance traveled by solvent front. So okay, next question. Suggest why the RF value is less than lidocaine. So you can explain this in two ways. Either that X is, you know, more attracted to the stationary phase, so it means, you know, in our silica it's more attracted towards the silica, or we could also say that lidocaine dissolves better in the solvent, probably because X is less polar. Yeah, because lidocaine is more non-polar, something like that. So I would just write lidocaine dissolves better in the solvent. Okay, next is NMR, nuclear magnetic resonance. Name the splitting pattern at 2.6 and 1.1. So 2.6, 1.1. This is very easy. Just count how many lines there are. 1, 2, 3, 4. That's quattro. And this one is 1, 2, 3. That's tri. So here it's just going to be a quadruplet because there's 4. Quad means 4. This is triplet. Tri means 3. The relative peak area of the peaks 3 and 2.3 is 1 to 3. Identify the protons and the 1H NMR that are responsible for the peaks. Okay, so we do have the formula of the compound there. Okay, so there are two things that I like to remember when I'm doing an NMR analysis. The first thing I remember is that downfield means deshielded, upfield means shielded. So downfield would be towards here to the left. So basically, the further you are to the left, the less deshielded that the proton is. So it probably means it's near to a functional group like an oxygen or nitrogen as you get to the left. So that's something that I like to remember. I think we're just gonna analyze the whole NMR here so that you know, we can understand what's actually going on. Okay, the fact that this is just, you know, very high, and it's 8.9, probably it's gonna be something around here. I would say 7.1 here. You have a multiplet. That means it has a lot of, you know, neighbors. 7.1, if I'm not mistaken, it's part of the aromatic ring. Am I correct in that? It's around there. I'm not too sure, but we're gonna work this out together. So the peaks at 3.0 and 2.3 are 1, 2, 3. So 3.0, 2.3. So 1, 2, 3. That definitely doesn't look like 1, 2, 3, but okay. The area shows the number of hydrogen actually. So that must mean the peak at 2.3, which could be that or that, is 3 times the size of that in 3. So what we're gonna notice here is that both of these peaks are singlets. So if this is you know a singlet, it means it doesn't have any neighbors nearby it. Maybe something that doesn't have neighbors would be this and this. Again, NMR is sometimes lots of speculation, but I would say probably 2.3 is this and this, because you have 6 hydrogen protons in total, and then here you have a singlet, no neighbors, no neighboring hydrogen atoms. So probably this one refers to 3 over here. Identify the protons. Okay, so when it's telling you to identify the proton, then you need to be very specific. What I'm trying to say is you need to be specific which position that it's on in the molecule. So going back to our analysis on 2.3 and 3, I'm pretty sure that this is going to refer to our number 3, and I'm also pretty sure that this is going to refer to 2.3. Reason being that 2.3 over 3 is 3, which equals to here, in this case, 6H over 2H. So perfect, we have 3. I'm pretty sure that's correct. The only thing we have to figure out is 7.1. And guessing on our chemical shift range, 7.1 could be here. So it's attached to the aromatic ring. Because I'm guessing, because there's a multiplet, I'm probably guessing that it's actually these on the benzene ring. This is just very characteristic of something on the benzene ring to be at around 7 and also have a multiplet. So we're gonna make it very clear. This is attached to an aromatic ring. This is the alkyl right next to CO, and 2.3 is going to be the alkyl on the aromatic ring. All right, so last question of this whole paper. Overall impression of the paper is, I wouldn't say it's that hard. I also wouldn't say it's that easy. It's I'd give it a 7 out of 10, I guess, on how difficult it is. But anyways, going back to the question, predict the number of peaks of a carbon NMR spectrum. So a carbon NMR spectrum is a little bit different from our hydrogen, but the concept fundamentally is still the same. Basically, we're trying to figure out how many different carbon protons there are. So if I would explain this briefly, let's say you have this magical compound over here, HCl. These are all 3 different carbon atoms. Reason this one has 3 hydrogens, this one has an NH2, this one has a Cl. They're all different. If I were to make this H, these two would be identical. Sorry, these two would be identical. So that's going to mean that you only have 2 peaks here. This is one type, these 2 are the other type. So we're going to apply that same principle. We're looking for how many different carbon atoms there are. I drew this out just so that it can be easier for us to analyze. Okay, so I think that's going to be pretty easy. Okay, so let's count how many types. I think this is the first type. This is the second type. It's on the, what is 1, 2, 3? It's on the 3 position of the benzene ring. This one's on the 4. They're different. This one is identical because this molecule is symmetrical, so that doesn't count. And then this one, it's an alkyl connected to a benzene ring. That's 3. This one, a ketone group, it's 4. This one is another one, 5. It's connected into one position and it's connected to an N. That's a different type. This one's a different type. It's jammed between a ketone and another N. This is going to be our sixth. What else? This is going to be our seventh here. Reason being, it's between an N, it's between an alkyl, it's different. This one has an alkyl connected to a CH2, so that's going to be our 8. One more I forgot is around here. This is on the 2 position, and it's connected to an alkyl, so that's going to be our 9. So there are 9 different peaks. And yes, I guess that's about it for this video. I hope you enjoyed it, and I really hope you learned something out of it. I apologize if anything was unclear throughout the way, but I really did try my best in explaining the concepts as much as I can in terms of what's going through my head. So thanks again for watching, and I hope you enjoyed it. This is Rico signing off.